Pleasure to introduce Fayçal Drissi, who's going to tell us about from Oxford University and the Oxford Mann Institute, and he's going to tell us about price formation and equilibrium, liquidity, and blockchain. So, Fayçal,
great. Thank you. Thank you very much. Hi, I'm Fayçal. Today I will be talking about price and liquidity in blockchains. I say blockchains and not automated market makers, and you understand why. And this is joint work with Agostino Caponi and Avor Cartea. These slides are online if you're interested in seeing them again, if you're missing my slides. Okay, so maybe let's start with a little bit of motivation. Perhaps money is a good motivation. So the decentralized exchanges are pretty huge with a lot of volumes. I checked this morning. And for example, in the last 24 hours, in all DEXs, there were something like $7 or $8 billion traded, so a lot of volumes. So you can imagine that yearly this sums up to a pretty good amount. And another motivation to study decentralized exchanges are that the fact that they work well is very important in the sense that it influences discussions on the design of these blockchains. Okay, and when I say decentralized exchange, I think of them as part of the blockchain. So automatic market makers have been studied a lot, and I think you will see talks about this in this the rest of this day and tomorrow. But perhaps to motivate this paper, I will talk about the blockchain protocol itself. And the blockchain protocol itself determines the life cycle of transactions from the moment they go from agent to the moment they're actually executed. And we'll see that it has a huge impact on actually how these markets work at the microstructure level. To give you a little bit of context, how do blockchains work? When you yourself send a transaction to the blockchain, how does it work? Well, the way it works is that every 12 seconds, throughout this 12 seconds, which is called block time, agents send transaction continuously to the blockchain. But they don't get executed immediately. They get into this memory pool, which is memory space where these transactions are waiting to be executed. And after 12 seconds, a validator gets selected randomly according to the blockchain protocol. And this validator takes transactions out of the memory pool and then creates the new block. And when the validator creates the new block, this is when exactly the market's clear. It means this is when transaction gets executed. Okay, so they are only pending in the memory pool. And when the block is created is when transactions are executed. Yes. Sorry? Yeah, that's. Yeah, that's a good, that's like my next slide. Yes. So everything is public. Yes, that's the most important thing, in fact. So when you send a transaction to the blockchain, you pay what's called the gas fee. And the gas fee has two components. One is, wow, I'm very bad at this. One is the base fee, right? And the base fee is given by the blockchain protocol. And it's based on congestion, but it's based on a rule. And if you don't pay the base fee, you're not even considered to be executed in the next block. Okay, and then the second component is the priority fee. And the priority fee is important because it incentivizes validators to give priority to your transaction. And this is how it works. Okay, let's say I'm trader one. Okay, here. I send my transaction to the blockchain with a $1 tip. Okay, at the very beginning of this 12 seconds, which I will call block time for the rest of the talk. So at the very beginning of the block time, I send a transaction with $1, and then Seb comes at the very end of these $12 and sends a transaction with $4 as a tip. Well, what happens when the validator or the miner gets selected and they create the block? Well, they will execute Seb's transactions first, even though he came after me. Okay, and I will be executed last. And in terms of consequences on the microstructure of this market first is pre-trade transparency, because everything that's going on in those memory pools, the level of priority fees, the direction of the trade, the quantity, and everything is public. So there's pre-trade transparency. Before trades are executed, everything is public. And the second thing is priority gas auctions. So Seb and I, during these 12 seconds, we can fight each other by overbidding. Okay. So yeah, there's these auctions, these online auctions where we fight for priority. And there is existing research on AMMs and decentralized exchanges and blockchains, but perhaps in the interest of time, I won't spend too much time explaining every paper, but there is a trend of literature that studies AMMs in isolation, like if they're not on the blockchain, like all I've told you basically doesn't exist. Then there is some empirical papers about what is the impact of all of this in terms of price and liquidity. And then there's some theoretical work about specific aspects of all of this. So in our contribution is to basically present a general model to describe the microstructure of decentralized exchange within the blockchain infrastructure. And with the focus on, we try to characterize the economic consequences of priority fees, the fact that we have to fight for a priority, and the impact of block time. So how long does it take for us to be fighting before the block is created? And we want to characterize the consequences of these two things on liquidity, price discovery, and market frictions. Perhaps I added the slides this morning to give results if I don't have time to finish my talk. But perhaps to summarize before reading all of this is priority fees are good for markets. Block times can be good and can be bad. So that's the big picture. Okay, so a little bit more detail. First thing, yes. Block time is
longer block time.
Longer block time. Yeah, longer block time. Yeah. The longer the block time, it's depending on the environment or it could be good, it could be bad. Okay, so a bit more detail. First, what we prove is that information is disseminated in blockchains discretely, because we prove that in equilibrium, traders will only reveal the true information at the very end of this block time. Okay, so this is in contrast to traditional markets where information dissemination is continuous. Another thing that we show is that priority fees have strong effects on the level of liquidity in these markets. In particular, we show that when there is an increased number of informed traders that are actually competing for Q priority, then the effect of priority fees is that it increases their costs and it reduces their trading volumes. And because of this, priority fees basically reduce the adverse selection losses of liquidity providers, and this increases liquidity in the market. Okay, priority fees also have effects on price efficiency. We will see that we endogenize the number of informed traders that are actually competing for this Q priority in blockchains. And what we see is that the presence of priority fees actually reduce the number of informed traders that would enter the competition, obviously because it's extra costs. And that reduces price efficiency. Price efficiency means how much private information has been disseminated in the price, okay? In terms of block time, it also has effect on price efficiency. What we show is that the longer the block time, the more prices can diffuse, of course, and it means that the expected speculative rewards of informed traders increase, okay? And what it means is that in equilibrium, the number of informed traders that actually enter the market increase, which basically improves the informativeness of prices. But it also has an effect with respect to liquidity, but here there's a trade-off, okay? What we will show is that block time, as block time gets longer, what happens is that there is a defensive mechanism by liquidity providers who want to protect themselves, so they reduce liquidity. But there's this other two effects, which are that as block time gets longer, what happens is that it gives more time to an informed liquidity demand to aggregate, to accumulate. So this has the opposite effect of actually adding liquidity, okay? Because liquidity provider want to make money from this uninformed demand, lucrative demand. There's a third thing is that as this block time gets longer, as I told you, the number of informed traders that want to compete for speculative rewards increases, right? But then the priority fees kicks in, and this actually, oh, sorry. I'm clicking without, yeah. And this actually, makes, yeah, exactly, supply grow. Okay, so that's an overview of results. Let's see how we prove this. Yes.
Your markets at a break.
Sorry?
Sorry, does your market ever shut down because of that?
Yeah. So there are actually two cases. One where when the cost of information is low and markets are liquid in terms of how many uninformed traders there are. In that sense, as block time grows, market gets more and more efficient. When I say efficient, at the moment they clear, right? Not throughout the thing. So they get more and more efficient in terms of liquidity, but also in terms of how informative the prices are. But then in the opposite context, then yes, there's at some point a point where market just completely shut down because liquidity providers cannot make money on average, right? So yeah, so I'll get into these details just afterwards. Okay, perhaps the model. So the general features of the model is that we consider a decentralized exchange for a risky security Y and a reference security X. You can think of Y as Microsoft and X as dollars. The marginal price, the initial price, is V0 that will normalize to 0 without any loss of generality. And I will call the future liquidation value in the AMM as V. So that's the future price, random price of this risky security that I can trade at later on. Liquidity supply in the AMM is kappa. So I won't say exactly what it is, but if I have time at the end of the talk, I will try and motivate this number, what it is exactly. But it's related to this convexity that you've heard in the first talk by Johannes. And if the liquidity supply in the AMM is kappa, then the cost to trade a quantity delta is delta over kappa plus pi. Pi is this transactional fee that AMMs charge, right? So it's a small percentage of the quantity. And this is the slippage, right? And 1 over kappa, you can think of it as the convexity cost again. Okay, so if I want to trade a quantity delta, this is what I pay. You can think of it as the spread that is quoted by the AMM for a quantity delta. And no, I mean, you have to multiply this by delta to get this is the unitary cost. Yeah, this unitary cost. So it's quadratic in delta when, in terms of slippage, and then delta pi. Yes? No, the base fee is normalized to 0. Pi is so every time you trade in an AMM, they take a very small percentage of your trading volume and take it away. So that's the pi. Yeah, base fee is normalized to 0 because all traders that are competing have to pay it. So without loss of generality, we just get rid of it. Okay, so instantaneous impact of a trade of quantity delta is 2 delta over kappa, which is also related to the convexity, and you've seen it very quickly in the equations of Johannes in the verse talk. But what it means is that once you have this quantity kappa, which is you can see it as the amount of money or amount of assets that are in the pool, you can know what is the slippage for trading a quantity delta, but also what is the impact once you've traded on the marginal price.
So you're assuming small trades.
Yeah. It's actually approximation. This is why my plot is here, is to say that this is an approximation, but this is using something like 6 or 7 million transactions from lots of pools. So yeah, so this approximation holds for a little bit less for larger trades, but sure, you can use it. Yeah, right. So this is on the here. This is the slippage, and that thing is the price impact of trades. Okay, so we can use this model to basically describe what is the slippage and what is the impact. I will assume an economy with 3 types of agents. 1 liquidity supplier, a representative liquidity supplier, a universe of informed traders, L, larger than 2, and then uninformed traders with elastic demand. Okay, so 3 types of agents. And my model would be a 3-stage model to describe basically the strategic interaction between suppliers and takers of liquidity in the blockchain. At stage 0, there will be a subset M, smaller than L, of traders that will actually pay a fixed cost C to acquire or to observe private information. So this cost C, you can think of it as setting up a blockchain node, buying some private data, or anything that you have to pay for to actually be able to engage in speculative trading. Okay. Then at stage 1, there will be a liquidity supplier that sets the AMM's reserve, which means setting up this number kappa, of course, based on rational expectations about what's going to go on in the future. And then at stage 2, there will be these M-informed traders that actually decided to engage in this competition that will compete among themselves with priority fees to for queue priority in the next block. Okay, so they do it for 12 seconds. And one very important property of this competition for priority fees is that you can only increase priority fees. Okay, so once you send a transaction to the memory pool, if you want to revise, you revise upward. You cannot revise downward. Okay, so after these 12 seconds, after we finished competing, what happens is that the validator will create the block and sequence the transactions by order of priority fee. Yeah, of course.
Within this 12 seconds, what information are they receiving in order for them to do this revision of?
Yeah, so for now, these are the general features. I will go stage by stage and explain what's going on. But I mean, short answer is they observe dynamic information and they decide that. But you'll see that it's not really relevant. You'll see why. Okay, so obviously the model is solved backward. And we'll start with stage 2. And I will describe the specific assumptions of stage 2. Okay, at stage 2, remember that we know the number of M traders that decided to enter the competition, and we know the level of the supply in the AMM. This is taken as given by the informed traders. It doesn't mean that it's fixed and not strategic, because when we do backward, these things will be a function of what's going to go on here in stage 2. Okay. My traders are risk neutral. Simplifies everything. So, I mean, I can do a linear quadratic approximation of a Cara utility if you want, but it will lead to the same thing, but more complicated. Okay, so my traders are risk neutral, and I'm also assuming that in stage 2, only informed traders are competing for queue priority. Why? Because liquidity provision is known to be kind of passive in AMMs, and also because it simplifies a lot. So when you look at data in AMMs, you see that something like 90 or 95% of the number of transactions are actually liquidity takers, and the rest are liquidity providers. So that's a way of putting it in the model. It's not endogenized, but we're forcing that only informed traders are competing for queue priority. I'm making some assumptions. First, that informed traders are observing some kind of a dynamic signal. Each of them have their own private source of information, okay? And my assumption is that from the perspective of me as an informed trader, the signal of other traders, the variance of these signals is evolving with time. So as block time gets larger and larger, longer and longer, the variance of the signal at the end of block time will be longer, right? So this is a kind of a picture to illustrate this. Okay, and same thing from the perspective of a liquidity provider. From the perspective of a liquidity provider, if the block time is longer, then they know that by the end of block time, the signal will have more variance. Okay, so I, as a trader who's competing for queue priority in the block, I'm paying a cost for information that is C, and this includes setting up a node. Okay, and if you know anything about setting up a node in a blockchain, then it becomes easier to participate in the blockchain protocol. So I'm just assuming that if you are an informed trader, then you're participating in the blockchain protocol, which means validating blocks, and that gives you rewards. Okay, so I'm calling this beta as the proportion of informed trader with respect to all other nodes. So beta is between 0 and 1, and R is the blockchain reward for the next block. Okay, it's fixed. Everything is fixed and known. So throughout this block time, these 12 seconds, informed traders can submit instructions to the transactions only when they are executed, instructions otherwise, to the memory pool with priority fees. And I will call this capital T as block time. I will model competition throughout block time from 0 to capital T as an online auction with a hard close, okay, where traders can only revise upward. And at capital T, they have one final opportunity to change their priority fees. And that's going to be a first price sealed bid auction. First price because the highest priority fee, the highest bid wins the auction. And all the other, and if you don't win the auction, what you do is that you just pay a 0 priority fee. Yes?
Why not
that's a good question. It leads to the kind of the same results, but if you do an OPay, then you have to care about, even if you lose, what is your order in the losers.
Yes, so I can understand first price when you have two informed people.
Yeah.
Okay, you do care about your ranking within sort of the M informed people.
Yeah, so one thing that you can do in these dexes is to send the limit price. So you can actually send an order with some given priority fee, but if you don't respect the limit price, if you traded at a worse price than what you wanted, it doesn't execute. So that's a way of saying, I'm sending with this priority fee. If it doesn't get out, if it doesn't get executed, then I can have another transaction that gets in then, right? And with zero priority fee. So there's a way of implementing first price yield reduction. In fact, that's what happens most.
So in the payoffs for your informed players, when you have more than two informed people,
yes,
you only care about winning, and if you lose, you're randomly shuffled within the rest of the
perfect. Yeah, you could have written the model. This is exactly what happens. Yeah.
As an informed person,
yeah.
there's five of us.
Yeah.
We're all trading in the same direction.
Yeah.
If I lose up being first, I want to be second still, no?
Yeah, I mean, again, doing this just complexifies stuff, but it captures, I mean, the first price yield auction captures the general microstructure stuff. So we did the model with an all pay auction. You have to kind of have the likelihood of being second, third, fourth, but that gives you like, a sum of order statistics. Exactly. Yeah. Instead of just one, but it is the same thing. Yeah. So just to simplify, it's a first price yield auction in the sense that if I lose, I don't want to fight anymore. I just like whatever price I get, but I'm not paying the priority fee. Yeah, but it's a very good question. Okay, so I will call this tilde phi, the largest bid from the online auction. So I'm, again, working backward. Remember that the final step is the first price sealed bid auction. And I assume that at the end of the online auction, the largest bid there is this tilde phi. Okay, I will call the private signal of trader I at the moment we arrive at the first price sealed bid auction as VI. Okay, and I will assume that it's drawn from some distribution F over some interval. Yes.
So another thing. So
yes.
In the beginning, it looked like in the net pool it's visible. In the beginning, it looked like in the net pool it's visible.
Yes. Yeah.
And then here it's missing.
So yeah, sorry. So we have so competition through block time. I model it as two auctions. One that is an online auction. And at the very end of block time, we have this last opportunity to actually revise our priority fees. And in that sense, once I revise, people won't have the time to actually see it. You see, yeah, so it's just the final round. Yeah. Good question, though. Yeah. Okay, so I will call this tilde phi as the largest bid from the online auction. I told you that VI is the private signal of trader I, and the private signal is basically just the expected future liquidation value of the risky security conditional on my private information. Okay, so VI is what I use to value the price, to value the security in the future. I will call phi I the priority fee of trader I. Remember that we are at the very last round on the first price yield auction. And I will call this delta I the trading volume of trader I. And in equilibrium, the strategic behavior of traders is not only the priority fee, but also how much they will trade, how much volume they will actually send in the transaction. Okay, I will make this assumption that all informed traders are either buyers or all of them sellers. Why? Because if I'm a buyer, I know you're a seller, we're actually going to compete to lose in a certain sense, because if you sell, then you're going to impact the price in the other direction that is interesting to me. And that adds, again, we did the math for all of this and doesn't change much, because at the end of the day, the people that are all buying are competing and the ones that are selling are competing, So it's not a very restrictive assumption to think that all people are buyers or sellers. I will describe the game from the perspective of trader I. It's a symmetric game, so it's the same thing for any trader. I'm a trader I. I'm competing in this priority gas auction. This is the PGA against M-1 other informed traders. If I win, which means that if my priority fee is larger than all the other priority fees, then I get executed at the price V0 plus the slippage. Remember, the V0 is normalized to 0, right? Just to get rid of it. So what it means is that if I win, I pay the priority fees. I trade at this price. So because here I'm buying, I have to pay cash, okay? And I hold some inventory delta I, okay, that I value at VI. So this is the expected value of V from my perspective, which is VI. But I pay the information cost, C, and I receive a validation reward. Beta over M is the probability that I will get chosen as a validator. And in that word, I will earn R. So that's the validation reward. However, if I lose, my order is, as exactly as Patrick said, is my order will be randomly placed among the M-1 losers. And in that word, I don't pay the priority fees anymore. However, I get executed the worst price. And what is this worst price? Remember that I told you that 2 over kappa is the impact, instantaneous impact of a trade of quantity delta. So here, I have M-1 over 2, which is the average number of people that will be before me. But I have a +1. Why +1 is because the winner of the auction, okay? So all of this gives us, if I remember well, M delta over kappa. Okay, so there is the impact of people that got priority over me. And by the way, this is why we're fighting. We're fighting because if you trade before me, then you worsen in the price. Okay, this is related to what Johannes was saying at some point. But yes.
So whether you win or lose, presumably should somewhat depend on the value of the private signal that you get?
Yes, exactly, yeah.
So are you conditioning your expected value on the fact that you won and on the fact that you lost? And is it true that like
Are you talking about the difference between private value auction and common value auction or not?
No, if you have a common value auction, conditional on the fact that I win or conditional on the fact that I lose, that provides me with some information.
Yes, yeah, but this is you'll see that's a private value auction here. Even though it's the same asset, you'll see, I mean, here.
So you're using it as a private value auction.
It's not that I'm using it, it is a private value auction. In the sense that I'm not, I mean, as you'll see, the inventory here, which is this is why you're thinking it's a common value auction, because there's an asset and we all value it at we all value in the same asset. But here, if I win or lose, I have the same inventory, so that goes away. In a sense, I care only about the impacts, and the impacts I estimated with my signal. No, no worries, no worries.
No, it just seems to me that because I don't know the value, like I don't know exactly what the value of the asset is. If the highest bidder wins, then conditional on me being the highest winner, like I know that everybody else.
Yeah.
That's a little different with how the signal is identified.
Yeah, exactly. Yeah, exactly. I mean, you'll see. I mean, the V here, it just cancels out, right? We don't really mind about the value of the asset, but more about how much it will change. Because I hold the same. Yeah. Yes.
I guess this is that the conditional expectation of B doesn't change on whether I was the winner or the loser, or the winner or anyone else.
Yeah.
In the setup that you have, because the only thing that determines whether you win is the fee this additional fee that you buy, right? It's more buy.
So I mean, so are you asking the question or?
I'm asking the question.
Okay. Okay. So if I estimate the price using my signal and conditional on like winner or how you say, or I mean, again, the asset that I hold, like the inventory that I will hold, is the same if I win or lose. So any way I estimate it, it will disappear from the expected wealth that you will see in the next slide.
Okay, I have one more question.
Yes.
So you don't have any other validators, right? It's only the informed traders and
No, yeah, the informed traders are a portion beta of all validators.
Sorry, thank you.
Yeah. And by the way, so because you're talking about common value auction and private value auctions, so I mean, we have it in the paper, but here I made this approximation that I didn't want to spend time on, but since you're talking about it, so I'm making this approximation here that I'm estimating the impact of the trading volume of my competitors with my signal here, right? You would imagine that this should be the other people's signal, but in that case, it is a common value auction, it leads to very similar equations, slightly more complicated and like less readable. But then it's a common value auction because why? Because conditional on winning or losing, yeah, the estimate of the impact is different. So yeah, but we solve it in an appendix and it leads to very similar results. But yeah, we can continue the discussion afterwards. Still have 15 minutes. Okay, so I know my expected wealth if I win and my expected wealth if I lose. I do not observe the bids of other competitors. However, I can estimate the probability to win, okay, which is the probability of my priority fee being larger than all other priority fees. And the expected utility for me as trader I is, I'm a risk neutral guy. So if I can rewrite the equation that I showed you before, it's the expected wealth if I lose, if I don't compete, plus a surplus. A surplus is minus my priority fee plus this m delta squared over kappa, which is really is what I'm trying to fight for, which is the impact that I will that I will not have to pay if I ever win. And this m delta squared over kappa is what's called the reservation fee, which is the level of the priority fee that makes me indifferent between winning or losing the auction. Of course, if I pay this thing, then I have the same expected wealth as if I just lose and don't participate in the competition. But what I will try to do is to pay a little bit less depending on my signal. Okay, so this is why I call it the surplus. Yes.
Question about the little PI.
Yeah.
Does this depend on bar phi? Like if I bid.
Yeah. So the PI you mean?
Yeah.
The PI depends on var phi.
It does
On my yeah.
It looks like it only depends on the expiration, not what they
No, it depends on yeah. So I estimate pi I as the probability of my priority fee being larger than the others. I didn't put any structure yet, but you'll see that it depends on my signal, of course. Yeah. And my problem is maximizing my expected wealth with respect to my priority fee, but also my trading volume, which is very important here. I can interchange the order if I want because of my assumptions, this expected wealth will never explode. Okay, so this cross derivative with respect to delta I VI of my wealth is not zero, which means that my trading volume in equilibrium, my optimal trading volume will be a function of my signal, but the same thing holds for the priority fee. So my priority fee will also be a function of my signal. And in equilibrium, I will just call the optimal priority fee delta of VI and the optimal, the optimal trading volume delta of VI and the optimal priority fee phi of VI. Okay, and this G here will be, because VI is random, again, from perspective of trader I, they know their signal, but the signal of the competitors are random, right? And I know but that their trading volumes will be functions of their signals. So the trading volume of other traders are also random variables. And I'm just denoting G as the CDF of, the PDF of these trading volumes, okay? Once you fix delta I and optimize over the priority fees, what you're solving is this, and you have a trade-off here in when you increase the priority fee, what you're increasing is your probability of winning the auction. You're increasing this PI, but you're also decreasing the surplus that you're going to win if you ever win, okay? So you have a trade-off. And to solve the equilibrium, I'm just going to assume that all my competitors are playing the same strategy phi. It's a symmetric game. And I will assume that it's an increasing function of their signal. Of course, the more their signal is strong, the more they want to trade, okay? And the more they will be competitive. So I will assume that my phi function is an increasing function of the signal, in which case now I can write PI, which is my probability of winning, as the as G of phi minus, as the probability of the inverse function of my priority fee being larger than the second largest priority fee, because the probability of winning is the probability of my priority fee being larger than the second largest priority fee. But the second largest priority fee, because phi is an increasing function, is the second largest signal. Okay, so I can just do the inverse. And I know the distribution of the second largest random, the second largest trading volume is this G to the power of m minus 1. Okay, so I know how to estimate my probability of winning. So I can just plug it here and take a first order condition, which gives me this. And this is a standard first price sealed bid auction with m players. Here, this m delta square over kappa is my reservation priority fee, which makes me indifferent between winning and losing. And this thing, I apply a discount to it, and this discount gets larger and larger with my actual signal, because the larger my signal, the more likely it is that I'm actually the largest, the person with the largest signal. So I apply more discount because I don't have to compete that much. Okay, standard. And the priority fee is an increasing function of the trading volume, and it's in decreasing in the liquidity depth. Of course, the more there is liquidity in the AMM, the smaller the impact of my competitors' trades, and the less I want to compete with them. Okay, because it's not that much that I'm losing. Okay, and if I fix the volume delta, remember that delta is a decision variable. But if I fix it, then the priority fee is increasing in the number of informed traders, because the more people are competing with me, the larger the expected impact of their trades if I ever lose. So I need to compete more with them. Now I'll come back to this online auction. One thing that you can prove is that the partial derivative of your priority fee with respect to the largest priority fee that has been observed in the online auction is positive, which means that the largest the maximum priority for the online auction, the more I have to compete, which is normal, right? But we can also show that the expected wealth of trader I is a decreasing function of whatever happened in the online auction. Okay, hi Bruno. Okay, so my expected wealth as a trader I, so which means the expected wealth of any other of my competitors, is a decreasing function of whatever we did in the online auction. So obviously, we have zero incentive to bid anything during the online auction. Okay, so when you solve back in the online auction, the priority fee is whatever the initial reservation priority fee is. If you remember, that was the base fee that's been normalized to 0. So I'm just going to consider that the online auction, nothing happens in equilibrium. Traders delay bidding until the last moment. That's a very important consequence on price formation. It means that information is disseminated only at the very end of this block time, okay, which is in contrast with traditional markets. And this is also what you observe in data. So here on the left, you have time to inclusion, which means here when you see 0, it means that it's less than 1 second between the time the transaction hits the mempool and the time is actually included in the block. And you can see as time inclusion approaches 0, more and more people are actually sending the transaction, but perhaps more importantly is the level of these priority fees. As you approach the end of block time, people send larger priority fees, okay? And if you read the paper of Caponigi and you in 2023, you know that larger priority fees are usually associated with more information. Yes, of course.
This is different from traditional markets, but isn't this quite similar to what we saw for the closing auctions before the exchanges made the cutoff random? So that people would also.
I wanted to skip this slide in terms of time, but now you're asking the question of the slide. It is very much related. The difference really is that the pre-opening sessions are a uniform price auction. Everybody is traded at the same price. It's not completely public. There's only like partial information that is public. And whereas here it's discriminatory and it's based on how you're sequenced. But yeah, you could think of the fact that markets only clear at the very end is what is very similar. And in fact, there's a rich literature around this, and basically our results just support this pure noise hypothesis of BA, Hillion, and Spad, who said that it's either these trades that you observe in the pre-opening session and closing auctions are actually just noise. So, but what we're trying to say, yes, it's noise, and we have empirical support from traditional markets from this pre-opening session and closing auctions that actually show that there's, I mean, the bulk of information comes at the very end, just right before the markets close, even though there's like this structural differences between these two auctions. But yeah, it is related. And I never said it's different, very different for traditional. Probably I said it, but I didn't mean it. Okay, stage 2, trading volumes. We still have 2 other stages. Okay, trading volumes. Yeah, so once I solve for my priority fee, I can plug this back in my optimization problem. I can, now I have to solve this optimization problem for my equilibrium trading volume. And here it's basically a trade-off between cost and speculative reward. Cost, because I have to pay the execution cost that scales up with how much, with the volume I'm trading. The price impact, which also scales with how much I'm trading and also reduces with my probability of winning the auction. There's also this priority fee pi delta I that also scales up with how much I'm trading. So all of this is making me lose money. However, I will hold an inventory delta I VI, and that gives me incentive to actually trade. And that gives me basically the equilibrium trading volume, which increases with the signal for two reasons. One is because I'm holding something that I value, but also because the larger my signal, the more I will apply, if you remember, a discount to my priority fee, because it's more likely that I win. So this like two reasons why my trading volume will increase with the signal. And then if I fix my trading signal and I make the dispersion of my competitors' trading signals move, increase or decrease, well, as this dispersion increases, my likelihood of losing the auction actually increases. So this makes me trade less, okay? Yeah, and the equilibrium priority fee, if you remember, is a function of my trading volume, but my trading volume is a function of my signal. And when you think of the priority fee at strategic, for strategically adjusted trading volume, then you can see that my priority fee is actually decreasing in the number of traders that I'm competing with. Why? Because the more there are traders, the more I have costs, and I will actually reduce my trading volumes. And if I reduce my trading volumes, I want to compete less actually. And this is basically our result shows that people with priority in the block have larger trading volumes, and this is what we see in data. Yeah. Okay, so liquidity supply. I'm a liquidity supplier. I'm balancing two things: with earnings from uninformed traders and losses from, very classic losses from informed traders. I will skip the details, but this is the equilibrium liquidity supply. And obviously, it increases in how lucrative the uninformed trading flow is. And it reduces in how much I'm expected to lose to informed traders. And that scales basically with the variance of their trading signals. Because the more there's variance in the trading signals of the informed traders to which I'm supplying liquidity, the more it is likely that I will lose money, because it means that the price is diffuse and maybe to more extreme values. Sorry, I have to rush through this. So one interesting point is that the liquidity supply increases in the number of competing informed traders. Okay, so there are many papers in traditional microstructure that show that basically try to argue that the more informed traders there is, the less liquidity supply. But then you have other papers that do the inverse. But here in indexes, we have a result that basically says no. When there's more informed trading, there's actually an effect of stabilizing the total volume of these traders, okay, and pushing the variance of this volume to zero, which means that from the perspective of a liquidity supplier, they like the fact that there is more informed traders competing with priority fees. Okay, I will skip all of this. Yeah, and that comes back to your question, Patrick. When you fix the number of informed traders, when you don't allow that number to go to infinity, then actually there is a level for the variance of trading signals. And if you remember, I told you that variance trading signals is somehow related to block time. The longer block time is, the more you have variance in the signals. And that basically we have a result that shows that block time has some kind of a threshold beyond which markets completely shut down. Information acquisition, very briefly, markets benefit from more informed traders in terms of price efficiency, but not in terms of volume. The more there are informed traders that actually pay the cost to observe private information and disseminate it in the market, the better, the more efficient the price. Okay, and what we see is that there is basically a trade-off between, for a given number M, what is my expected revenue as an informed trader when I'm stage 0, knowing what the liquidity provider will do and knowing how we will compete in the future. Well, you can compute basically at stage 0 what your expected wealth for a given number of informed traders. And basically, to endogenize the number of people that will actually pay this cost C, you just take the expected future wealth, right? And it has to be, and you prove basically that it's decreasing in the number of people that are competing. Yes, I know. And basically, once it hits this constant cost C, this is where the equilibrium point is. Okay, and yeah, long story short, I mean, I'm not gonna show you a slide, but maybe just listen to me. But long story short, what we show is that as block time gets longer and longer, informed traders are more incentivized to enter the competition. And then you have, sorry, yes. And then you have two scenarios, actually. You have one scenario where this cost of information is high, where the cost of information is high, this one, and this N, which is the volume of uninformed trading, is low. Well, in that scenario, as block time increases, the effect of the defensive reaction of liquidity providers from this adverse selection losses actually surpasses the effect of priority fees that reduces the speculative rewards, okay? And markets shut down. However, if this cost is low and this N is high, which means that there is a lot of uninformed trading happening, well, then the opposite happens. Actually, as block time increases, everything is better in terms of more informed traders have entered the game. Liquidity suppliers add liquidity because they will, what they earn from uninformed demand is actually way higher than what they lose to informed traders. And in that sense, the longer you have, the longer the block time, the better the markets once markets clear. And this is in complete contrast to this wide push of reducing block time by computer scientists. And I think I will stop here. Thank you.